So Rami, I'm going to go ahead and switch the screen over to yours, and you can take it away.
Thank you, and thanks for the invite there. So I'll talk a little bit about how we're implementing Akka.NET at Hyperview. Have a couple of slides there. One is a little bit about me. I've been in technology for a long time. I got introduced to computers when I was in high school. I don't know if anybody remembers the TND TRS-80, but that's where I started, with a little cassette deck and kind of a very old version of BASIC. But I mean, and the rest has been history since then. A little bit about Hyperview. We co-founded Hyperview to build the tools we wished we had when we were managing data centers. It's built as a digital infrastructure management platform with a focus on data centers, but it could be applied to other types of smart infrastructure. The company was started as a kind of a future looking at with the assumption that all future digital infrastructure is going to be distributed. It's going to have a high degree of instrumentation, and we need a single pane of glass to look at that. And right now, there is a lot of kind of fragmentation in the tools market for organizations managing distributed digital infrastructure. We're headquartered in British Columbia, Vancouver, and the team is distributed between Vancouver and St. Louis, Missouri. And our mission is to make critical infrastructure think. So now onto Akka. So some of the problems as we were writing Hyperview was written from scratch. And after we had a first generation product, and which was more of a traditional client server architecture product, .NET 4.5.2. And so we took it back to the drawing board in 2017, and we started rewriting the system. And one of the things we wanted to do is build it for the future. And as things arised, we wanted a back-end processing system that managed the types of data we were doing. So we had a bunch of system requirements. So system requirements dealt with, multiple data pipelines. We had a data pipeline that dealt with various types of analytics, be it numerical analytics for sensor values. Another one is generic data analytics that deals with the data coming in as we do automated discovery of digital infrastructure on networks. And that required a kind of a pipeline with logical steps and forks in the road as to where the data goes. Does the asset exist, or does this thing exist that I'm looking at? Is it a new thing? Has it changed? And so on and so forth. So that was one requirement. Another requirement is dealing with high-speed scheduling of operations. And we had also a requirement where things needed to run in a certain order. So you'd have a lot of high-speed atomic operations. Let's say you're just kind of serializing a lot of sensor values to a time series database, but then those sensor values can then, once serialized, needed to be extrapolated and analyzed further to extrapolate more data, which then can allow you to extrapolate more data, and so on and so forth. The last piece was we were dealing with a lot of incoming events. So we listened to events coming in from the data center. The most classic event would be, for example, an SNMP trap. At the time, we adopted a version of 1.x, .NET Core. We started kind of building the system with it. We saw .NET Core as a future. We were looking for performance. The system needed to be performant. It needed to be scalable, maintainable, and flexible. So all of these kind of big goals for our system. And because we saw ourselves building this and maintaining it for at least 10 years. The other thing was the type of data we were dealing with. We were dealing with millions of events per day. I know Aaron is dealing with millions of events per second, but the types of events we're dealing with are over disparate networks. Like, you got, remote networks, you had network latencies to deal with. The size of the event could be multiple megabytes. The data it carried. If you're doing a scan on a very large switch, you could be dealing with 10, 15 megabytes of data that you needed to analyze in a single event. The data was diverse in size and in type, string data, numeric data, XML data, etc. And it was, we had different pipelines where you had kind of, for example, a steady flow of data coming in from monitoring, for example. And you had bursts when you're doing scans or when you had a trap storm, etc. So that you needed to deal with.
What's a trap storm?
So it's essentially if you had a bunch of SNMP, let's say you had a failure of a switch or some sort of a failure in a data center, and you suddenly all of these machines are going and sending you events. Hey, this happened, this happened, this happened, and so all of these kind of machines are sending you SNMP traps that you need to kind of receive and process.
Gotcha. Okay.
The other part is that we had events that could trigger other events. So, for example, a classic one would be a user interaction. A user changes the location of an asset, and so location metrics would change. Simple thing would be you have a server in a rack, you move it from one rack to another. Now your calculations on the amount of space available in the rack is different, which cascades to the availability of space in a row, which is available, and availability of space in a room, and so on and so forth. So a lot of cascading events that needed to happen in a certain order, because one thing has to happen before it triggers the other thing. We investigated a lot of options. We had a lot of familiarity with schedulers. I mean, we used Hangfire, and Hangfire is a very fine scheduler if that's what you want, and very good piece of software there. We looked at schedulers. We also looked at rolling our own code. And in fact, we started writing our own event-based, like classic .NET event-based system. And we looked at others. And just by a kind of a fluke there, I was listening. I was either Hanselman or .NET Rocks, and I think Mark Rosinovich was talking to the podcast host at the time, and he mentioned something about Akka and how he would use it for distributed applications. I'm like, let me check that out. So at that time, I went in and on a weekend, I kind of looked at Akka. I went to the website, did the boot camp. That's very interesting. And I started kind of evangelizing the system internally with the team. And, before we knew it, the team saw it as kind of a viable option, definitely better than writing our own framework for what we were doing. The rest is history. We did actually, investigate a generic, generically the actor system, and there was Orleans at the time, but Orleans was not available for .NET Core at the time, so that's one. And two, I really found the developer accessibility and features in Akka much more. Much nicer, and easier to kind of work with. I haven't looked at Orleans since then. I don't know if things have changed, but that's it. The rest is history. We adopted Akka, and then we kept going.
What sorts of things about Akka.NET did you and your team both like specifically in terms of the developer experience?
For me, everyone has their own opinion, but for me, the logical consistency of the framework. So I can easily talk to my CEO and describe what we're doing. I can look at the code and walk people quickly through what's happening, and at least for me, and it was okay. This is what happens. This is what, and then this is how the data flows, and this actor does this, and this actor does that. And it's very easy. So, and also that fast forward to now as we're training new developers, it's very, easy for us. Let's say we're adding another analytical actor. It's very easy to come in and just say, okay, here is where we're keeping everything. This is what you need to do. This is the the class that you need to inherit. You implement it here, and then things just work from there. That's it. I would say that's the biggest thing. It's just very logically consistent and accessible and easier, at least for me, to develop with. So.
All right. Thank you.
Okay. I think I covered this. One thing I want to note as well is that it did support our use cases, so it covered all of the things. If we needed a scheduler, it was there. If we needed pub sub, if eventually we want, it's there. If we, so all of our, if you need to schedule at a certain time, you could use a Quartz actor. If you needed to poll, it's there, so on and so forth. It definitely supported our use cases. There was a lot of batteries included functions there. So right now we're doing fine with just a basic implementation. Our implementation is not fancy at all. I do want to look at Akka streams at some point, but if we wanted to do Akka remote, we could. If we wanted to do more with persistence, we could. If we wanted to scale actor systems, we could. I really liked the fact that the community was active, and I really liked that we had the option of commercial support as we grew, and with PetaBridge, and on the open source side, I really liked the engagement from Aaron and the team on that side as well. So there was a lot of goodwill and activity there that allowed me to say, okay, well, let's goodwill in the community. It's an active community, and I have all these extra batteries included features for the future. So it's that kind of weighed into as well the decision moving to Akka. So any questions so far, by the way? Okay, I'll talk a little bit about the Hyperview architecture, and I'll jump into how we're using it. So Hyperview, this is our reference infrastructure or our reference architecture design for the platform. And Hyperview is a set of microservices running in Kubernetes. We designed the system to be scaled independently depending on functions. So depending on the customer use case, customers that had mostly a monitoring use case needed more data collection endpoints, so we could scale that microservice independently. Customers that had a lot of need for the data services APIs and the management APIs can scale that independently, and so on. So that was one of the tenets of the design. The other part of the design is that we tried to keep the data where it needed to be put. So we have a central application database, and then everything else resides in auxiliary data structures that manage the persistence of the data. So we're using PostgreSQL for our primary database. We're also using things like Redis. We're using blob storage. We're using Elasticsearch, and so on. And each one of those serves a specific function in the application. So it's very much distributed. We have auxiliary cloud services that we've built for data enrichment. That's our catalog service. And customers interact with the database mostly from the web UI, but they could also interact with command line applications and from CLI applications as well. So internally, in terms of the interactions, all of the Akka services are built as backend analytical services. There's no user interaction. So they run in the background. They take orders from a message queue, and they're interacting with the data persistence layer. And the primary pipelines for us are discovery data analytics. One of the tenets of the design of Hyperview is intelligent infrastructure discovery. And that's where you can scan your digital infrastructure. We collect all this data, and then we try to guess, oh, that's a server, this is a switch, this is a power distribution unit, this is a sensor, and so on and so forth. and we instantiate all that data into the system. There's a lot of analytics that goes in the background in terms of things like deduping data. Is this an asset that has multiple IP addresses, or are these two different assets? Is this an asset? Is this an IP address that gives me information about multiple assets, etc.? So there's a lot of data. Is this an existing asset or a new asset? Has it changed? What changed? And so on and so forth. The next piece of data is sensor analytics. So not only do we receive sensor data and serialize it, but we also analyze it, calculating all of the statistical inference and statistical calculations, and we also look at things that can be extrapolated from that sensor data. We look at the sensor data. We look at filling in the gaps so that the data can be normalized. We also look at basically the linkages of those sensors in relation to where they originated and what information they can give us about the infrastructure. So all of that stuff is happening in sensor analytics. A lot of internal jobs that happen from batch operations, be it just something as simple as mark these assets as retired, or delete these assets, or etc., to external jobs where you have long-running operations that synchronize to ServiceNow, for example. And so you've got some very short-lived actors, you've got some very long-lived actors, you've got some very short-lived jobs and very long-lived jobs, and everything in between. You've got jobs that hand data to other jobs with messages, and you've got routing actors that figure out, okay, I need to call this actor versus that actor, and so on and so forth. Looking back at over the since 2018 till now, in terms of the challenges and the learnings, I'll start with the learnings. I think the most important part of the journey has been the team, essentially, just making sure that the team has time to understand the framework. Most developers that I work with are not familiar, don't even know what an actor system is, let alone Akka. They may be really good programmers or developers that understand other frameworks and other types of design patterns and so on and so forth, but it is going to take them time to wrap their head around what is an actor system, how does that work, so give your team time to learn it. The other part is try to phase in the work. Don't try to do everything at once. Don't try to do, import everything from the framework and try to make it work. Just, you need a schedule actor, do a schedule actor. You need a receive actor, do a receive actor. Make sure that works, and then make sure everything is running. You're meeting your business objectives or your functional objectives of the code, and then build on that. There's no need to introduce complexity if you don't have to. And gradually introduce features. Don't introduce everything at once. Don't ask for everything at once. And essentially just try to build things up. Have a solid foundation and layer your features. So these were my primary learnings. And in terms of the challenges, as looking back over the last few years, wiring up tests was initially very interesting. Back in 2018, there was some documentation. Things didn't work as expected. There were some differences between Linux and Windows. We had tests that were consistently passing on Windows that were consistently failing on Linux, for example, for no reason. I had no idea what was happening, but things kept working. Okay, well, what was going on? So we had things like, okay, well, how do you deal with dependency injection? Do you even need dependency injection? You just kind of wire things up very simply, like small actors that do specific things versus like kind of larger actors that do more complicated things. Those were big decisions. How do you do and required spikes and kind of figuring things out. It turned out, yes, we do need dependency injection. There was a lot of kind of services that were written and a lot of abstractions that were written in the application. It's a very large application. I don't want to kind of replicate and rebuild. So dependency injection was very important for us. So wiring it up correctly was absolutely paramount. Lucky I worked with a fantastic team that was kind of able to figure that out. Database context, especially if you're dealing with the data, if you're mutating data within the actor, and how are you passing your DB context between actors? Do you need to do that? Do you reinstantiate the DB context? How often do you do it? You've got a long kind of a long-term kind of a long-living DB context and short-lived actors. You've got long-lived actors, and you don't want a short-lived DB context, and so on and so forth. So managing that, and also the effect of the ORM. We like entity framework. We use it across the board, but I think a good question is, like, do you even need entity framework for some of those? Like, would a lightweight, more lightweight system like a Dapper work better? So these are kind of big decisions or early decisions that you need to experiment with to make sure that you understand. And specifically with the DB context, you just got to be very careful there. Differences between Windows and Linux we covered. Cutting edge versus bleeding edge. So you want to be on the cutting edge and not the bleeding edge. So somebody told me that. And we were kind of on the latest version of .NET Core, like 1.1 or whatever at the time. And we were early adopters of 2 and early adopters of 3 and so on and so forth. So every time we do that, there were kind of like little frictions and things that you needed to figure out. And some NuGets didn't keep up that you need to kind of make sure they keep up in the stack. This is not necessarily an Akka thing, but we did see things like deadlocks that I believe were more bugs in .NET at the time than in Akka. Then we kind of worked around them by locking to a specific version of Akka at the time.
Well, speaking to the when you were talking about writing up tests, some of the weird behavior where things passed on Windows and didn't pass on Linux, we definitely ran into early on.
Yeah,
with like the early versions of .NET Core, some pretty big behavioral differences where I think the way .NET Core was architected at the time is it was largely p-invoking down into native libraries underneath the surface, whereas a lot more of it is managed today, where it's all written in managed code. And that's kind of tracked concurrently with, let's say, the Roslyn analyzer kind of getting, not Roslyn analyzer, the Roslyn compiler kind of getting a bit more sophisticated. And there's still definitely areas where both runtimes still call into native code. A good example of that is the socket libraries is one example. But yeah, there was definitely some weird differences early on that took a while to smooth out. Moving to .NET Standard actually simplified a lot of things because some of the platform neutral libraries were just not available in .NET Core 1.1. A good example of that is the way we implemented coordinated shutdown was something that only worked on .NET Framework, didn't work at all on .NET Core because that app domain exit event was not included in the first 2 versions of .NET Core. It wasn't until .NET Core 2 came out that they added a bunch of those old APIs back. So there was definitely some churn from a platform perspective back during like 2017, 18, in the early part of 19 probably. But yeah, I remember that well. And then, in terms of gradually introducing Akka.NET and not trying to bite all of it off at once. So, I know you guys you're only using core Akka right now for the most part, right?
For the most part, it performs really well. It does what we need it to do. But I mean, looking forward, we are eyeing Akka streams. We are eyeing to introduce Akka in other parts of the product, specifically on the data collection side, and potentially some persistence. We haven't really needed persistence, and or clustering.
And you haven't really needed persistence because most of the state management, in terms of like the events, is all handled by the durable queue the Akka.NET reads from, right?
Absolutely, that's what happens. So everything. Actually, there's a little bit of learning there. We use Redis as our durable queue, and it's high performance. It does what we need to do, and there is a bunch of logic in terms of catching exceptions, certain types of exceptions, not all, of course, but and requeuing and so on. So that allowed us to manage things. We also do things like turn off the faucet and just restart the actor, restart the containers, and then turn them back on. So the opportunity for data loss is extremely minimal at this time, so that kind of allowed us to reduce the complexity in the code and to need another persistence layer. I do see the value, and I think eventually we'll be moving towards that as the actors get more sophisticated. But yeah, that's what we're doing right now.
Well, and that approach makes perfect sense. One of the advantages of Akka.NET over something like Orleans, for instance, is that from day one with Orleans, you're building a distributed system. That's what it's built for, and that's how it's modeled and architected. Whereas with Akka.NET, you can start with something that's designed to operate as a single process, even potentially an embedded process in something like a mobile app, if you want to. And so in your case, the types of calculations and everything you need to do, what Akka.NET's basically responsible for, as I understand it so far, is that pulls these events from a Redis queue. It basically applies these sort of calculation models that you have, and maybe it pulls some data out of the database for each calculation that has to perform, produces the new value, writes it back into that database later, right?
Yeah, for at the high level, that's pretty much what it does. Yeah.
Yeah. And then you also, of course, mentioned you have like a staged event-driven architecture in a couple of areas where one calculation might might have a side effect on another calculation downstream, where it's kind of like a cascade. It's kind of like a calculated cell in Excel where you change the original value, then all those values cascade, right?
Yep.
But it makes perfect sense that you can kind of start with something really small and like just like Akka.NET in a single process, get familiar with the actor model, understand how to model flows and protocols and messaging, which is honestly where 90% of the learning curve is, and not introduce things like serialization or remoting or clustering or persistence just yet. And Akka Streams, by the way, is probably the next best stop on your journey. So if we're going from local actors to streams, since that gives you a lot more control over flows in particular. So if you wanted to do things like implement batching, or you wanted to implement debouncing, or you wanted to implement, let's say, rate limiting inside your system, that would give you sort of a very succinct way of doing all that. And then the only point where it would begin to make sense for using something like clustering in your case would be if, now the way I understand it is Hyperview's software is basically embedded into customers' data centers, right?
No, it's all running in the cloud. It's all running in
all
Azure.
Running in the cloud?
The only thing that is in the customer database is the data collection
gotcha.
system.
So the telemetry agents.
Yeah, so essentially just a very lightweight application running on Windows or Linux that handles the data collection. Everything else is running in Azure.
And so in terms of your scale out on Azure right now, do you guys provision basically like a set number of processes per customer, or do you have just one process handling everybody, or sort of how's that sort of done today from a scale?
That's actually a very good question. One of the things that allowed us, or actually allowed us to not need things like a clustering system, is the fact that we can take every customer gets their own namespace and their enclave inside Kubernetes and their enclave inside all of the database services and stuff like that that can be scaled independently. So you don't need to provision a large cluster. Every customer gets the standard deployment, and then they scale out based on their needs from there.
Gotcha. So it's your multi-tenancy model in terms of how you're basically kind of doing that at the level of Kubernetes infrastructure rather than needing to do it inside your app. That makes sense.
Yeah.
Gotcha. Well, that keeps things really simple in this case then from an app design point of view. All the infrastructure that you can go ahead and model for one tenant, you can essentially replicate it on a per tenant basis, right?
Absolutely. Just add it to your Helm chart and then, just run it again for that customer.
Well, that's very cool. And that's, that's basically like your clustering is basically just happening at the Kubernetes level instead of within your actors and everything else.
That's right. And it also allows us to neatly and to claim and to say to customers, look, your data is isolated. It's not intermixing with anybody else's data, and which is and it kind of keeps things nice and neat, and it kind of gives us a little bit more flexibility on that side.
That makes sense. And then in terms of you mentioned the dependency injection and DB context issues. So my first and only major piece of downtime with the first ever production AkkaNET application, which was, guess what? A multi-tenant analytics and marketing automation service that I built. My only source of downtime was dependency injecting a Cassandra equivalent of a DB context and having that exact problem where the actor lived forever, but the DB context was automatically pooled by the database driver every 60 seconds. So we had done all these load tests and everything else, and where we were blasting tens of millions of events at the system, but none of those load tests ever ran longer than 60 seconds.
Yes.
So as a result, we deployed into production for the very first time. Everything looked great until the 60-second mark, in which case our error rate spiked to about 10,000 errors per second, and the number of bytes written to Cassandra fell to 0.
Yes.
And it was basically because, all those objects were all disposed, and every time the actor restarted, it was getting the same disposed context passed back into it. So this is before we wrote. This is before we wrote a real DI system for AkkaNET. By the way, this is like early 2014 when this was all happening.
Yeah.
But that's definitely a common problem. And the new AkkaNET dependency injection library, released a little bit over a year ago, allows you to inject those service scopes into your actor, which you can go ahead and essentially destroy and recreate like on a per transaction basis if you needed to. So that'll go ahead and open and close your DB context. But yes, that's an example of a problem that a lot of people, including myself, had very early on. So I'm not surprised you guys ran into it. But hopefully our literature is a little bit better at addressing some of that stuff now.
Yeah, I mean, it's been getting better. I mean, all of these issues have since been addressed, but yeah, we've seen some weirdnesses in there. Another thing that we saw like back in the early days was if you had a database exception for some reason, kind of gets or puts the DB context a little bit out of whack. Nothing saved at that point. Nothing saved. So kind of similar to your Cassandra issues. So interesting times, but it works. So I'll move on to the next slide. Let's see what. So it's just general things that we saw and learnings. Concurrency was a big deal. Managing concurrency. How many actors do you instantiate in a system? Do you need 10 actors? Do you need 100? How are you? How many? Especially with Postgres, like how many database connections do you have? To do that, do you need something else in the infrastructure, like a PG bouncer or whatever, to manage the all of these incoming actors connecting to the database? And understanding how concurrent you need to be, how often you need to poll, and playing with those numbers is extremely important. Looking in the rear view mirror here and making sure that you run those on a long-term basis. Those scenarios on a long-term basis to understand where the data and where the bottlenecks are. Latency and bottleneck management is important as well. And Hyperview is an eventually consistent system. So you're designing for eventual consistency, and part of understanding your eventual consistency is really understanding where you want your bottleneck to be. Is your bottleneck on the event side? Is your bottleneck on the number of actors? Is your where are you queuing things, and so on and so forth? And designing for those bottlenecks. The worst thing you can do is not understand that and having this moving bottleneck where you fix one thing and it kind of pops up somewhere else. And you kind of constantly running, figuring out where things are stopping and how they're stopping. You fix one bottleneck, it pops up on the database. Now the database is starved. And so on and so forth. So understanding your latency requirements, and designing for a bottleneck is important. We did see things like in relation to latency and concurrency is things like locking, and I'm not talking about mutexes or thread locking or things like that. I'm talking about, okay, you're working on an asset, and this asset was discovered by two data collectors. You got the two messages, they got processed at the same time, and now you're instantiating the asset. But then one kind of the two actors doing the analysis are blind to each other because none of the data has been serialized to the database. So the system is designed to deal with that. But just understand, you kind of, as you're dealing with data, how the data is coming in, where your race conditions might be. Do you need to implement any kind of, for the lack of a better term, a business lock, on an asset while an actor finishes work versus the other, and so on, if that's needed. Debouncing or deduplication of work is important. You don't want an actor, you don't want to keep repeating the work, and that's one of the things that actually makes streams batching and debouncing or deduplication is one of the things that make Akka streams interesting for me. Is okay, now you need to kind of update your caches, but you got 10 changes that ask you to update your cache, but you need to really update the cache once. So you know what? If an actor picks up the update cache event, look for all of the update cache events, deduplicate them and do it once versus, do it 10 times. Retry logic, and when do you retry and when not to retry, and specifically around things like, you got an exception, whether it's a network exception or a database exception, whatever. It's a distributed system, lots of things can happen. Is it okay at some point to say, you know what, this event's going to trigger again in like another 50 milliseconds. I don't need to do anything, just kind of destroy the actor and move on. Another one, no, this is important data, I need to requeue it, and then, do something and then pull it back. So understand that in your architecture and figure out when you need to retry and when not to retry. And that kind of relates to exception management a little bit. Infrastructure is, for us, infrastructure capacity is very important, making sure that you have, if there's two levers to this, is like how much you want to spend on infrastructure and how you're built for infrastructure. Let's say you're using Cosmos DB and you're built per transaction, and you're doing 250,000 transactions per day constantly, then you're going to be paying a lot of money for Cosmos DB. So
Cosmos DB and Azure Application Insights are just total like money pits, basically.
We saw a spike in Cosmos DB billing. And we actually re-architected around Cosmos DB. Not that it's a bad database, just the way it worked for us, it just wasn't feasible to continue to use it because the number of events and the number of times you're doing things is just going to grow, and it's just not going to be feasible to continue to use it based on the billing structure. So we used the kind of a distributed cluster of Postgres servers, and kind of that helped us quite a bit, and kind of reduced. It ran really well. It runs really well, and it just helped us to do that. But we had the flexibility to do that. It was early on in the process where we could make the change. Like if we had a petabyte of data in Cosmos DB, it would have been a completely different conversation at that point. So what else? So just be, how you're laying out your infrastructure, what are the billing levers, what are the bottlenecks in terms of, network performance, CPU performance, RAM, etc. These also impact things. Akka actors, especially when you're like, if you get a large discovery coming in and it's all network information, you could have like, thousands of files each, 10, 15 megabytes each that need to pass through memory and be analyzed by the actor systems. How are you bursting your actors, and how are you managing, dealing with memory management with Kubernetes and so on and so forth. So just some of these considerations there.
That's another area where Akka streams could definitely help, is throttling. all that stuff. Yeah, definitely.
What else? Just that's pretty much sums it up. Overall, been happy with Akka. We want to grow with it. We want to implement more features, and just wanted to thank Aaron for such a great product and for continuous support the continuous support of the framework. So in open source.
No. We're happy to do it.
And the team, of course.
Of course. Speaking of the team, do any members of the audience or Gregorius, do you have any questions?
No, everything's clear.
Looks like we don't have any questions in chat at the moment. I guess, so my next question would be in terms of your infrastructure today. So are you guys running on .NET 6 now? Or are you still using .NET Core 3.1? What does that look like?
Yeah, we try to be in lockstep with whatever Microsoft does. So we're on .NET 6 right now. .NET 7, I'm not sure if we're going to be using it yet, but the team tries to be current. So .NET 6, latest libraries, latest entity framework, and latest Akka as of a few months ago.
Well, we should be getting a new beta of AkkaNET 1.5 out onto NuGet officially sometime soon, which should have some of those new .NET 6 dual targeted features. Would definitely love to hear your feedback on whether or not it affects performance. Although it sounds like AkkaNet's fast enough where you may not even notice today. But you never know.
Yeah, you never know.
Yeah, you never know. So I'll definitely be keen on your feedback from that. Lastly, do you want to put up your contact information in case there's anybody in the AkkaNET community who maybe is looking for a job or maybe wants to get in touch with you, some technical questions?
Yeah, absolutely. So Hyperview, that's the website address. Feel free to visit and contact us. Contact me on LinkedIn any point. I am not hiring right now per se, but I'm always recruiting. I'd love to meet Akka developer. Hit me up on LinkedIn and introduce yourself. I'm more than happy to connect and so on. It's always good to meet good people. That's it.